Hello and welcome to the 8th lecture in chapter 22 in our comprehensive course on AI, ML and DS. Now, the topic that we are at present handling is feature selection techniques. And we saw that there are three categories of feature selection technique. One is called filter methods, another category is called wrapper methods, and yet another category is called embedded methods. We also did one example of filter method first, that is select k-based features. Then we did three more examples of filter method earlier in the last lecture, right? Now, in this, that is last was this mutual information based filter method, right? Now, we also did one example of wrapper method, which was recursive feature elimination. So now we want to do some more examples of that wrapper method. And these initial steps are just repetition. So I will quickly just go through them. Here we import the library in the data set and print the data set. So this is my data set, and you can see that now both, if you write df is equal to data.frame, then you can say that it is having both features as well as target variables, right? So now both features and target variables, they are present in my data set. And now I want to convert it into, from this left side format, currently I am in this format where I have a full data set from which I want to separate by a vertical split, so that features are separate and the target variable, that is median house value, that is separate. So for which this is the standard way, that df.drop columns is equal to median house value. That means keep all columns except median house value, drop that column. That would become x. And second, y is equal to keep only median house value. So then that will give me x and y. Then you divide once x and y are obtained. So that means now I am at this stage, okay? And then you divide x, that is the green colored rectangle, further into two parts. Say 70% in the train set and 30% in the test set. So this becomes x train, this becomes x test. Similarly, divide this y also into the two parts. So 70% in the train set and 30% in the test set. Okay. So this is y train and y test. And then first let us print them. Here we are doing one extra step also. We are scaling the train sets. So that is x train and x test. Remember that there is no need to scale the response variable. We only scale the feature matrix. So scale them, and we can print the output just for viewing. So this is my x train, okay? That is this data set. First printing x train. Then next is, this is my y train, okay? So that is this data set, this dark yellow like that. Then this is my x test. So that is this lower green, and this is my y test. That is this lower yellow part, light yellow part. Okay. So that much steps are very common. First, you just have to prepare your data. Now, actual feature selection starts from here. We had done one recursive feature elimination method as the example of wrapper method. Now we want to do two more: forward feature selection, backward feature selection, and also what you call recursive feature elimination. One more example we will do, because at that time when we did the example of RFE, at that time we took only 3 columns for simplicity as the original data. But now I am taking all the columns, and I am trying to do the same RFE also. But first, forward feature selection. Now, whether you do forward feature selection or backward feature selection, from sklearn you have to import sequential feature selection only. So just the way you adjust it hyperparameter, one will make it forward and another will make it backward. Okay. So otherwise both are sequential feature selector. So we will see that. But first, what is sequential? So in forward feature selection, what is done is, we start with one feature, only one feature, and we make a machine learning model like y is equal to beta 0 plus beta 1 into x1, only that much. And we make one machine learning model. Then next time we add one more feature. So now there are two features, x1 and x2, and we make machine learning model y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. Then next time we will add one more feature, and again y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, and so on. Ultimately, you will go on doing this for one by one, go on adding each feature until all features are exhausted. Okay, that is called forward feature selection. So you start with one feature and go on adding other features, right? But other way of doing this also is there, that is called backward feature selection. Now in backward feature selection, you do what? You do take all the features right from the beginning. So that means all 8 features. So here this would become y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus beta 5 x5 plus beta 6 x6 plus beta 7 x7 plus beta 8 x8, where this is my x1 first feature, this is my bit x2 second feature, x3 and so on up to this is x8 eighth feature. So I take all the features in the very first model, that is also one method, and then I go on removing features one by one. So remove this. So now I will be left with a model which has only 7 features. Then remove longitude and latitude both. So now I am left with 5 features, rather 6 features. Now remove longitude, latitude and these also. So now I am left with 5 features and so on. So go on removing the features and go on measuring the accuracy of your machine learning model. And whichever set of features gives the best accuracy, select that many features as the important features for predicting variable. Okay. So I am trying to predict this. First forward feature selection I am doing. So I will go on adding features. So sequential feature selector SFS. So let us create one sequential feature selector object. Model is equal to model. Now here I am using linear regression, but one can use random forest or other model for which you have to import corresponding, because random forest you will not find in linear model, random forest you will find in ensemble model. But that is okay. Then you can use that also, but I am using simple case linear regression. And then sequential feature selector, and the model is model, that is this linear regression. Direction is equal to forward. Scoring is R square. That means the parameter which will decide the goodness of model, that is R square. Cross validation fold is equal to 5, and n jobs is equal to -1. That means how many different combinations you have to take. Then take all possible combination, or there is no limit. -1 means no limit. So the process will continue until all features are exhausted. So first this will be added, then 2 will be added, then 3 will be added, and until all the features are exhausted, right? So that is how this process will do. Now this is just an object created with certain traits, but now you have to fit that object on your X train and Y train. So if you fit that object on X train and Y train, then you get features is equal to SFS.fit X train Y train, and then get feature selected. Now rest of the code, that is not that important. It looks very complicated code, but actually it is just a simple code which says that one by one go on taking each feature and go on adding them in the list, empty list which you have initialized, that is the current features. So current features is equal to 0. Then select various features and append it to this list. So one feature which you will select first is, say I write one column here. What are the feature names? Okay, just for so that I don't have to scroll so much. So here, these are my feature names. And one more was longitude. Okay. So I will go on selecting these features one by one and go on appending them in this empty list. Okay. So these are my features, and I will go on adding them in my empty list. And each time I will measure R square, because my scoring parameter is R square. So I will measure the R square of the model, and I will go on noting down. While this just plots the figure, just for better visual understanding, that as I go on adding feature, how my R square will change. So this is not at all important. This whole thing, that is not at all important. Okay. But it is just for better understanding. So this takes some time because plotting is also involved. So you can see that here some asterisk is there, and now it is done. This is a nice plot which shows clearly what is happening to R square on Y axis as I go on adding different features. What were my features? Here I have pasted them. So these are my features. I am also pasting them below at the end of the code so that they are visible. So median income, that is the first feature which I took. Then next time I added house age. So here whenever house age is written, that means now I am taking 2 features, median income and house age. So R square is increased. Now I take these many features, 3 features. So median income, house age and latitude. Then R square further increases. And then I take latitude, so not average rooms, but median income, house age and latitude. And similarly I take median income, height, house age and longitude also. So the 2 features here and 2 features here. And I got the highest possible R square, right? Thereafter, the whole plotting process stopped. That means you can say that as far as this forward feature selection is concerned, this is nearly the peak value. So that means it is not possible to get higher than that. So final R squared is equal to 0.5931. Okay. Now why I here 2-3 points are important, which I want to explain. One point is that this is highest with forward feature selection, but this is not necessarily the highest possible value of R square. If you have chosen linear regression here, which is the most elementary algorithm for predicting a continuous variable, so that's why you are going only up to 0.5931, right? But you can choose a better algorithm, then your R square may be much better. Second thing, here the process stopped at 4 features, but you can score for all the features. So this is that line of code, model.fit X train Y train, and take all features R square and let us see what you get. So this shows that even if I would have taken all the features, and these are all the features, right? So even if I would have taken all the features, still my R square would only marginally increase. Here I got 593, okay, or 59.3%, and here I got 596 approximately. So that is 59.6% R square. So the question is, for increasing the R square only marginally, is it sensible to go from these 4 features to these 8 features? Then it is not at all sensible. This R square may look good, but that is only because it is at present performance is being measured on the test set and train set. But when some totally unknown data set will be found, then it might be that the model will not generalize well. So overfitting might have occurred by taking all features. Okay, so that is one thing which I want to show. And the forward feature selection, that means automatically kind of stops when you when it feels that now onwards if you add one feature, then the increase would be only marginal. Okay, so that is fine. Now next reverse process is backward feature elimination. As I said, at that time what you do is you do take all the features, and in the beginning you take all the features, these are all the features, and one by one go on removing the features. Okay, so that is also sequential model only. So that is why I have not shown that initial part of data creation and importing library and all that. We are using same California data set and X-train, Y-train, and X-test, Y-test, and X-train skilled and Y-train skilled, but and imported the same library. So we directly, I am showing from model is equal to, or SFS, even model also I am keeping same for sequential linear regression. So I am showing from this. This was the code for forward feature selection. Instead, this is now the code for backward feature selection. Okay, so this is backward feature selection code, and here I have kept the code very simple so that you just understand that all these things, this code was looking complicated, but that is because of this frill that I wanted to plot the diagram showing increase in R square as each new feature is added. But if you don't insist that, then it is in just 4 lines of code. SFS backward object you create by sequential feature selection. Model is equal to model, so that is equal to linear regression, and features to select. Here you are deciding how many features you want to select, because initially you have taken all the features, right? So from which how many you want to select, how much simplification of model you want to do. So that in features to select is 5. Direction, previous one was forward, here backward. Rest of the things are same. Scoring algorithm is scoring matrix is R square, and CV cross 5-fold cross validation. And then SFS backward, this object which you have taken here, that you will dot fit into on X train and Y train. But here you see one important difference, that for backward we have to use scaled X train, but Y train is as it is, right? That is just some quirks of various different algorithms. And then selected features you find by X dot columns SFS backward dot get support. And once you get that, then print that selected feature. So just 4 lines of code, and you can see that these are the 5 features which you have selected: median income, house age, average bedroom, latitude, and longitude. Previous I selected only 4, and I got median income, house age, latitude, longitude. Here I am getting all same, but only 5 I am selecting. So average bedrooms is one feature which is added. Now here also, if I want to add all those frills, then I can do all those filling, and that means create one empty list for score, create one another empty list for removed features, and then one by one go on removing feature and go on finding R square, go on storing them in this R square in this list, and also go on plotting the figure by which will display the performance also, and with removal of each feature. But here you see one important thing, that is this, that when you initialize your SFS backward, num feature to select, that you are taking 1. So that means that you are going all the way. So here num feature to select is 5. So that kept these 5 features. But if you select 1, then what will happen that you see? Okay. So if you do, this is how things are happening. This is the R square when all the features are kept. Here on x-axis number of features are there. Okay, and here all the features are kept. Then one house age is removed. Sorry, this first I think, yeah, house age is removed. That is this case. Then average rooms is removed. That is this case. Average bedrooms is removed. That is this case. And the R square keeps on decreasing. So it is clear that as you keep if you keep all the features, you will get maximum R square. But keeping all the features is never advisable, because these are your features, right? So if you make a model with 8 features like this, then that model will surely overfit, and it will not be generalizable. So then you have to make compromise, that get ready with some little bit of reduction in R square. Here it was somewhere 0.61 or 62. Okay, now here you take it to 61 it is, okay, because the gap is of 0.02. So this is 0.62. Now here that is 0.59. So okay, I can get with that much R square. Here also it is 0.58 point something, so nearly 59, and here also it is above 0.58 or say nearly 0.59, so it is okay. But thereafter it in fact R square marginally increases. So that is also an interesting case, that you can see that actually this average occupancy, that feature, or when it was removed, this population was removed, then at that moment the R square marginally increased. Okay, so this feature was perhaps negatively contributing. Okay, and one can see here one big drop. So if on removing a certain feature such big drop in R square is seen, it is 0.62, from which directly you are coming to 0.48, less than 0.48, so around 15% drop in R square is seen, then you will say that it is not wise to do this drop, or that means it is not wise to eliminate this feature. So you can select these five features. Okay, if you want to select four, sorry, then you can select, yeah, five, because median income was there here. So then you can select the five features up to this. Okay, but don't select the other one. Okay, so then that is one way of interpreting this graph. Now here this dotted line shows the optimal number of features. So you can say that six features appear to be optimal. Okay, that means even this many are not required, because the six features will give you sufficiently high R square also, and still you will have reasonably less number of features. But still, if you want to remove, insist on removing, and if you can handle a little bit of reduction in R square is acceptable, then maybe even just four features up to this population, that is also fine. Okay, now selected features are median income, house age, and average rooms. So there, wherever that dotted line is there, whatever is that feature, median income is not annotated here, but median income is also the very first, it is the most important feature. And house age, so here house age was removed, and here average in rooms were removed. So this reduction suppose is not acceptable to me, then I will say that I will use this many features, right? So these are the selected features, that is median income, house age, and average rooms. And R square I am getting 0.5894. So in forward feature selection, as you go on adding feature, R square goes on increasing, and clearly that means the maximum value of R square you will get if you keep all the features. But as I said, that model will most likely overfit. Similarly, here this backward feature selection, here as you go on reducing the feature, R square goes on decreasing. So again here also, when you keep all 8 features, you get the highest R square. 7 features slightly less, 6 features slightly less. But you have to decide that up to what limit you are willing to tolerate reduction in R square. And suppose I have selected that these are the optimal number of features. Okay. Now, though recursive feature elimination we had already done RSE, but we are again doing this RSE for all the features, because when we did RSE at that time, if you remember, our original data frame had only these columns. Rest of the columns we did not consider. So this time I am considering all the columns of my data set, and I am doing that recursive feature elimination. Now that steps I am not showing, because those steps are same. That is these steps I am talking about, that you first import the data set. This is my original data set. Then you divide it into x and y. Then you divide it into x train and x test. That we have already done. And this x, y, x train, y train, all these x train scaled, y train, x test scaled, these are already present in my this environment. So I will directly show the steps which are next for the recursive feature selection, right? So from sklearn, feature selection, import RSE, initialize the model, some model you have to use, so linear regression model, and perform the RSE. So max features you decide that x train dot shape 1. So that means that number of columns inside, that is your maximum features, right? So then this is how you initialize perform RSE. So RSE estimator equals a model, number of features to select is equal to 1, and in one step of one feature at a time. And RSE dot fit is equal to x train scaled y train. And here also these all lines, they are just extra frills that are added. So even if you can't do these lines, then it is okay, because I will show you that original code is only this much, and here below you just have to print the results by one line of code. Okay, that is the last line here. This last line is that selected features or optimal features or whatever, that last line of code you have to keep. But I want to show the graphical process also, what happens as you do recursive feature elimination. So that is why plotting a graph is always difficult, but that is only for conceptual clarity. Okay, so as you see this, you can see that recursive feature elimination goes on adding feature, but or you can think from this way, then it is removing, eliminating features. So first it starts with all features, 8 features. Let me make slightly smaller in size, right? Okay, so it starts with 8 features here, then 7 features, then 6 features. Up to that you can see that R square, which is plotted on y-axis, remains above 0.6. So that means it looks fine. Even with 5 features, R square is 0.6, so that looks okay. But thereafter R square starts decreasing. So it is up to you if you want to accept this much reduction, these reduction, and after this point, the reduction is very, very sharp and it directly comes to 0.25. So obviously such R square is not acceptable. So you have to select either this many, 3, or if you want then 4, or if you still want more features then this many. Okay, but that many features you can keep, or rather you can say that or keep all 8, or keep 7, or keep 6, or keep 5, or keep 4, but do not or keep 3, but do not eliminate more than that, because at least 3 features are very, very important, beyond which R square decreases. Mostly we keep it here only. So let us see what optimal feature, how many it has selected. Here it has selected 7. So that means it just stopped at this point where you actually where the plot flattened, because at that point it got maximum value of R square. So R square is maximum, and that is 60%. So recursive elimination is definitely superior. You are using same algorithm, linear regression, but with forward feature selection you got R square of somewhere 0.53. Right, that was, I think, this is forward feature selection, right? So it was 0.59. With backwards feature selection you got R square 0.58, while with recursive feature elimination you got R square 0.6. So that means 2% gain is a big gain, because you are predicting house value, and house value, you know that it is 4.653 and that kind of number, but multiplied by $0.1, rather $0.1 million. So just 2% gain in accuracy or performance, that will lead to a lot of gain in the from business point of view, right? Okay, now here what I was speaking is that suppose I comment out all these lines. All these lines were just extra frills. That is the word which I used. Okay, so comment out suppose all these lines. So then let us see what happens. I don't want to plot anything and all that. I just want to find the most optimal number of features. That means I am happy with this kind of graph. Then how much code will be required? Then only this much code will be required. That is this much. So you can see that it is hardly a few lines of code now. You are importing RAC. You select your model which you want to use. Then you select how many maximum features are there in your data frame. That is equal to the number of columns. Then your not number of columns, not data frame number of columns, but extreme number of columns, right? Then you initialize one RAC object. So RAC estimator is equal to linear regression. Number of features to select is equal to 1, and step is equal to 1. And then fit it RAC.fit xtrain scaled ytrain, and selected features RAC is equal to x dot columns RAC dot support. That's it. And in that many line of code, you have got your result. Okay. So if you plot it, then well, unterminated string, some small error is there. Don't worry about it. So what is happening is, yeah, here this f string is not terminated. Okay. So this is my f string. Okay. And if this is a printf statement, then it should be completed appropriately. So this is completed here. This is completed, and the printf statement is, yeah, fine. So you can see selected features only one latitude, and you can get the result also in this manner. This result shows at each and every step. Okay, R squared at each and every step, and final R square you will be able to see somewhere actually. Okay, I think it is the result of this. So let me just remove this line of code, because even after commenting it is getting printed. And let us for safety test it here so that I can make it like it was earlier. So I think what is the issue with this unterminated string, that issue will not come again now. Yeah, so selected feature is equal to latitude. Only this much code is enough to decide one most optimal feature. And you can select more number of features also. By here number of features to select. For example, earlier we had selected when you got that recursive feature elimination 0.60, then I think we selected 4 features, right? So number of features to select, I write 4. And then so these are the features: median income, average number of average bedrooms, latitude and longitude. So these are my 4 features. So only this much is actual code, but all that frill was required just because I wanted to plot the graph. So now I am pasting it again. And just checking, yes, it works. So fine, that means this is 7 features are selected, but if I keep only this 4, then you can see that it is this many features, right? Okay, now that is okay. Now this I delete because that was just temporarily. Now in next lecture we will do discussion about embedded methods. In embedded methods we have done one example, that is lasso CV. So now we will do example about random forest and XG boost, extreme gradient boosting. Now ideally this would be a little bit what you call premature to discuss because we are going to do a lot of detailed discussion on random forest much later on. In fact, this is how the course progresses. Any course or any standard textbook you see, first linear regression is introduced. Simple linear regression. Simple linear regression means the simplest possible case where y is equal to beta 0 plus beta 1 into x1. Okay, only that much. So that much will be introduced first. Thereafter, multiple linear regression will be introduced. So that would be this kind of case: beta 0 plus beta 1 x1 plus beta 2 x2 plus maybe 10 variables x1 x2 up to xn, right? Then classification will be introduced. Then decision trees will be introduced. Then maybe KNN and other distance-based algorithms will be introduced. Then ensembles will be introduced. And in those ensembles, two most important ensembles are random forest and XGBoost. Okay. So that is why I'm saying that this would be a little bit premature. But anyway, we will do whatever we can at present, and you just try to uh, understand as much as possible. If you don't understand everything in this random forest and XGBoost, then don't bother at present. We also take another example of lasso. Okay, so that means we'll take 3 examples for embedded methods that we'll take in next lecture. Thank you and see you in next lecture.